All right, friends, Unit 4, this is the fourth lesson. We've combined several lessons. We combined the first 3 lessons into 2 videos just to kind of buy ourselves some time on the way to Thanksgiving. So this is Lesson 4. Lesson 4 deals with the most significant theorem we study all year. You can tell it's significant because it has within it the word fundamental. This is about the Fundamental Theorem of Calculus. The big player here is Isaac Newton. If you're reading the Finney-Domana-Waits-Kennedy book, there's a historical note on page 294 about Isaac Newton. Isaac Newton did more by age 25 than I will do in 3 lifetimes, assuming that I have 3 lifetimes, but that's neither here nor there. So let's talk about the Fundamental Theorem of Calculus. And when I mean the Fundamental Theorem of Calculus, I mean a theorem that's so big it comes in 2 parts. Today, I'm only going to deal with the first part. I'm only going to deal with the first part of the Fundamental Theorem of Calculus today. A second video will deal with the second part of the Fundamental Theorem of Calculus. Here's the way the theorem goes. If f is continuous on the closed interval AB. By continuous, we say continuous because that means that f is integrable. Then the function capital F of x, which is the integral from a to x of little f of t dt, has a derivative at every point x between a and b, and here's the kicker, the derivative of capital F with respect to x, which, just in case you're curious, is the derivative with respect to x of the integral from a to x of f of t dt, is f of x. The derivative of capital F of x, the derivative of the integral function, is little f evaluated at x. This is a big, big, big deal. So what I'd like to do is I'd like to illustrate what's happening here. I'd like for you to see some capital F's. And I think I can do that. Remember, capital F is some function that we don't end up seeing. So let's pretend that little f of x is a number. Let's do that nice and easy. Let's say it's 2. Let's say that little f is the function 2. And let's say that capital F of x is the integral from 0 to x of f of t dt. So I suppose to be proper, this should say little f of x is 2. But when we go over here, we use little f of t because the integral depends on the function f, not its input. Its input is the dummy variable. So in this case over here, x is the input into little f. In this case over here, the x is the input of our function. The little f is just along for the ride. So how do I generate capital F values? Well, at x equals 0, we're pretty sure we're at 0. Because at x equals 0, the integral from 0 to 0, well, that's a pretty thin rectangle. And then if I come over to x equals 1, the integral from 0 to 1, well, that looks like it's 2. And then the integral from 0 to 2, well, that looks like it's 4. And the integral from 0 to 3, well, that looks like it's 6. And so it appears that capital F looks like that. Capital F looks like a line. This almost makes sense. How could that line go into the third quadrant? Well, if we were to go to -1, the integral from 0 to -1, because we're reading right to left, takes the area that's positive and turns it around negative. So here's the question. What is the derivative of capital F of x? Well, the derivative of capital F of x appears to be 2. And 2 is little f of x. One more. Let's pretend that f of x, little f of x, is the line y equals x. And I realize that that's off there. And capital F of x is the integral from, I don't know, 1 to x of little f of t dt. Let's imagine that. Here, I'll even move that down there. Capital F of x is the integral from 1 to x of little f of t dt. So at 1, we are there, because the integral from 1 to 1, well, that's pretty much it. So what happens now? As I generate more and more area, it appears that my capital F is going to get larger and larger at an increasing rate. It's not easy to show that, but it gets larger and larger at an increasing rate, because as I go from 1 to 2, there's not as much area as there is from 2 to 3, not as much area as there is from 3 to 4. It appears that my F should be increasing concave up. If I go from 1 to 0, I've got to have some negative result. I've got to have some negative result. And then the most curious thing happens. When I take a look at the integral from 1 to -1, the integral from 1 to -1 has to be 0, because the positive area and the negative area cancel each other out. So what I end up with is a capital F of x that looks a heck of a lot like a parabola. It looks a heck of a lot like a parabola. And I'll bet my bottom dollar that if I take the derivative of that parabola, I'm going to get x. Seems reasonable. It seems like a reasonable thing. This is what the Fundamental Theorem Part 1 says. The Fundamental Theorem of Calculus Part 1 says that if I have a red function, f of t, and I create a blue function, capital F of x, that takes an integral from any constant to x of f of t dt, that capital F is differentiable, and its derivative is little f of x. This has two very serious consequences. Serious consequence 1. Every continuous function is the derivative of some other function. We may not be able to find it algebraically, we may not be able to explain what it looks like, but every continuous function is the derivative of some other function. 2, integration and differentiation, and I'm going to use a very bad word here, undo each other. It's in quotes because it's a bad word. It's not exactly what we mean. Integration and differentiation undo each other. If we take the derivative of an integral, we end up with the function we started with. I mean, it's not, they're not inverses of each other. It's not like they're reflections over y equals x, but they, to some extent, undo each other. So just so we're clear here, time to find some things. If I'm looking for the derivative with respect to x of the integral from 0 to x of e to the 2t dt, I'm looking for a derivative of an integral from a number to x. And if you have a derivative of an integral from a number to x, the answer is that function with this guy subbed in. It's the integrand function with the upper limit subbed in. And it doesn't matter if that number on the bottom is 0, if the lower limit of integration is 0, or if the lower limit of integration is some other number like -2. If I see a derivative of an integral from a number to x, then I know I'm taking this function with that guy substituted. Why doesn't that matter? Why doesn't the number on the bottom matter? Well, I'll tell you why that doesn't matter. Let's consider what would have happened if we created some other, oh, I'll go purple for this, if we created some other f function, call it f2, and it was the integral from 1 to x of little f of t dt. The integral from 1 to x of little f of t dt. Well, then at x equals 1, we'd be at 0. And then at x equals 2, we'd have an area of 2. And at x equals 3, we'd have an area of 4. And we would have this function right here, which I drew it badly, but you can imagine in your mind's eye, that looks exactly like the blue function. It's just been shifted. It's been shifted. How far? That far. That far. That green area is that distance right there. So the lower limit only affects vertical shift on a capital F graph. It does not affect derivatives because vertical shift does not affect derivatives. Is that okay? We're almost there. I got 3 to do. If I want the derivative with respect to x of the integral from 1 to x squared plus 3 of sine t dt, now I'm thinking to myself, I've got a derivative of an integral from 1 to a function of x. Well, I'm thinking that I just take that function and I substitute that guy, but then I'm reminded, wait a second, this is chain rule. Chain rule says if the thing I'm using right here isn't x, but it's a function of x, then I have to multiply by the derivative of the inner layer. Oh, yeah. Oh, yeah. Well, what if it goes the wrong way? What if the x is on the bottom instead of on the top? Well, that turns out to be not too big a problem, because if we want to turn it the right way, where the number's on the bottom and the x is on the top, all we have to do is say when we read this backwards, we have a negative in front. And so the derivative in question is just negative x squared minus 3. When we read backwards, there's a negative in front of our function. One more. What if there's x's on the bottom and the top? How do we handle that if there's an x on the bottom and on the top? Because the fundamental theorem only works from a number to a variable. So I have to break this up. And in fact, I'm going to break this up into the integral from x to 0. You could pick any function you wanted. And then from 0 to x squared. Why does that work? Well, that works because if I take the integral from a to c plus the integral from c to b, that's the integral from a to b. I know that that works. And so what happens? Well, the thing on the left reads backwards, so that's -1 over x squared plus 4. Good catch, folks at home. Plus, now I'm doing the integral from 0 to x squared, so that's positive. I sub in the x squared, but then I've got to multiply by the derivative of x squared. And then I leave it just like that, and I don't even try to simplify. Okay, that's the fundamental theorem part 1. Fundamental theorem part 1 helps us find the derivatives of integral functions. Fundamental theorem part 2 will help us to evaluate integrals, to evaluate definite integrals, and that is the part with which you are much more familiar. That is the part we'll hit tomorrow. All right, thanks guys.